IPv6. So, what the IPv6 is? It's the Internet Protocol version 6, which means there was already version 1, 2, 3, a long time ago, before 80s in previous century, forgotten, luckily. There was even version IPv5, developed for streaming by Apple. It was dropped, luckily for us as well, since it was basing on IPv4 as well. It didn't solve any of the issues that we are facing right now with the IPv4. So, current presentation is divided into multiple parts. First, I will tell you about why we should be moving to the IPv6, why the IPv6 was developed in the first place. Then we will talk about basics of the IPv6, then addresses on the interface, how to address the node in the IPv6 network. Next part is transition method, how to migrate from IPv4 network into IPv6 networks or in reverse. A quick introduction, a quick story about how Codillac introduced the IPv6 into its own network. Then I will be telling some slides about IPv6 and implementation inside the hardware of network devices. Last slide is who is using IPv6, and then there will be questions. So, let's start with the year 1981, and there were two famous declarations. First, someone said that 640 kilobytes should be enough for everyone. And the second declaration was 4 billions of IP address is plenty and should be enough for everyone. Well, with the first one, we know how it ended and how much memory currently the PC has. And with the second one, it went almost the same. Also, I can point out that even there were 4 billions, about 50% of the IPv4 address space was given to the multiple companies like AT&T, Hewlett-Packard, Apple, and they are not using that IP address space. So it's in cold storage, it's reserved, but no one is using. It's just being wasted. Okay, how it's looking right now. Since the IPv4 is limited, there is a limited amount of IPv4 addresses that has to be distributed or given in some way. Among years, up to five companies or 5 organizations were created: RIPE, ARIN, LACNIC, AFNIC, APNIC, and those companies were given some IP address space, and if you wanted to have some class of IPv4, you have to go to the organization, request some address space like /22/16, and in the most of the cases, you were given that address space. However, since the IPv4 is limited, as you can see on the right graph, those organizations quickly ran out of the IP addresses. So, you can see that APNIC, RIPE, and LACNIC and ARIN, they almost ran out. They are within the last /8, so they have less than 16 million of IP addresses. This is not much. This is not enough for current needs. And since they are almost out of the space, they have implemented special policies that I'm presenting here. And for example, APNIC, which is responsible from Indonesia, Australia, and China, they are giving no bigger space than /22. The same for the RIPE, the same for the LACNIC. The ARIN, North America organization, has totally run out of IP address. So they cannot give you anything at all, even if you really need, you are a telecom provider, you are a company, you want some address, they say to you, okay, we can put you online, and you have to wait. Maybe someone will return the address space, some address, maybe you will get it, or you can go, of course, to the black or gray market and you can buy the IP address. Of course, there is an Africa company There still have some in the pool, but the Africa is only for the organization inside the Africa. So you cannot get the IP from Africa to use it in Europe or in North America. You are limited to the continent you are currently in. So most of the companies are running out or already have run out of the IP address. So if you are telco or company or someone else, you are pretty much limited what you can get regarding IPv4. The other case that the IPv4 is running out is that at the first /8 were given. So one company was receiving 16 million of IP address, or /16, 60,000. So there were not much of the prefixes inside the internet. We can see here in the early the 90s, there were below 100,000 of address space of prefixes. Then, since a smaller and the smaller prefixes were given, desegmentation continued, and the flip size, the memory or the prefix, the number of prefixes in the internet were rising up. This creates problems. Each prefix needs a dedicated amount of memory. Each prefix makes the convergence time, in case of some issue like failover or switch over between routing devices, increases the convergence time. Also, the old equipment, I'm talking about really old, like Cisco 6000 or 7000, were limited by its memory or by its design only to 500,000 of IPv4 entries. So somewhere around, I don't know, like 2013, 2014, there was some issue with them because the internet crossed the threshold and those devices stopped working. They were dropping core, they were refusing to accept new prefixes, or they were just dropping the new old one in place of the new. Luckily, most of those devices were replaced, and newer ones have much more memory, but still, it's getting worse and worse. And right now, we are hitting like 700,000 of prefixes. So, in 1998, someone decided, some time ago, but in 1998 it was finally finalized in RFC. So they decided IPv4 is not enough. We need IPv6. We need something bigger, better, that has no issue that were introduced with the IPv4. So they have developed the IPv6 protocol. Since the 4 billions were not enough, they decided to have a little bit bigger address space, 2 to the power of 128. Of course, so the address changed. It's not compatible with the IPv4. Since there is so many addresses in IPv6, every IPv6 address is a public one. There are some exceptions, I will be talking about them later. Luckily, the support in the DNS were almost transparent. They introduced a new record, 4A, which means I'm requesting IPv6 address for the domain name. And you can do this request over IPv4 protocol. This slide presents the main differences between IPv4 and IPv6. As I said before, the address space in the IPv4 was limited. In IPv6, we have plenty of them. In the IPv4, the minimum packet size was around 500. In IPv6, it's a bigger one. Since the IPv4 had smaller packets, there was fragmentation, and the fragmentation in IPv4 could happen on sender or on transit device. Since the fragmentation is being done in hardware, the hardware has to be able to do so, and there were some issues. Plenty of them with different, like Cisco was limited to, if I remember correctly, 1,000 fragments per second. Huawei has some other issue with ACMP and so on. I can talk about this later on if you are interested. But needless to say, with the IPv6, the fragmentation in transit was dropped entirely. So if the device in between needs to fragment, it just sends ICMP message, hey, I'm not able to forward this packet, do fragmentation on your own. And then the sender adapts, sending smaller and smaller fragments. In the IPv4, the IP header size was not fixed. It was at minimum 20 bytes, but it could get longer. There could be some extra headers. There was an even special header inside, there was a special field inside the header named stating how long the header is, which creates some issues for the forwarding cards or forwarding routers, since any type of packet could be different. They have to be analyzed step by step to find which field responds for what. With the IPv6, it's fixed. Every field has its own place, it doesn't change. So if we are making offset of some bytes, we'll hit the source address plus 128 bits, we are hitting destination address. NAT. Since the IPv4 is running out, people started using NAT, Network Address Translation, to save some space. Of course, the NAT solves some issues and creates even more. One of the example, two devices behind the different NATs try to communicate with each other. They cannot. Of course, there are some countermeasure to work it out, like a stun solution, but it's difficult. In IPv4, we have something called broadcast and multicast. With IPv6, there is no broadcast. There is just multicast. Everything that was using broadcast in IPv4, in IPv6 is just using dedicated network space of dedicated group of the multicast. ARPs. With IPv4, there is something called ARP, to address resolution protocol, that provides provides connection between IPv4 address and layer 2 Ethernet MAC address. With IPv6, they drop the ARPs entirely and replace them with ICMP messages. The picture on the right, it's by Cisco, show us what classes, what fields are missing, the red ones, what fields has changed, the yellow one, and what fields has remained almost the same are the blue one. Since the IPv6 is a long address, there is some methods to make it shorter. Let's take a look at example A. We have a pretty long IP address, but when every octet between the columns, if it's begin with 0, we can drop all this beginning leading 0 entirely, and if then we have octets built only from 0, we are connecting them with columns. So with example A, we can make this address look like this one. The most obvious example is the loopback address. It's the first IP address with 1 at the end. Since there is only 0 before it, it's getting simplified to the column 1. Having not only numbers but also letters in IPv6, companies were able to play with it a little bit, like Facebook has address, face, column, book. Later on, I will be talking about notation of IPv4, coding IPv4 inside IPv6. There should be IPv6 here. So we can see this IP address, C0000201. It's, let's code this differently, and at the end, this is the IPv4 coded on 2 last octets of IPv6. So I will be using that notation just to keep things simple and not to make you recalculate the hex in your heads. IPv4, IPv6 addresses. There are some ranges that all of you should be aware of in IPv6. The first one is link locally unicast address. This is the address space that every device that has an interface with IPv6 family on it, that interface will already have IPv6 address assigned to it. That address will be given, the prefix will be like this, at the end will be calculated either randomly or from MAC address. I will talk about this a little bit later on the next slide. The second address range in IPv6 is a loopback address. We all know the 127.0.0.1 in IPv6 is just :1/128n, not /8 like in IPv4. I told you before that every IPv6 address is public one. Well, it's not exactly the case. There is a class /7 unique local address, ULA. It's equivalent of the RFC 1980 that's defined the classes for IPv4 like 10.0.0.0/8, 192.168.0.0/16, and so on. Those addresses are not routable in the internet. They are being used inside some networks for experimentation, for providing local connectivity over IPv6. The next address space is multicast range. Since there is no broadcast, there is only multicast. The range is pretty huge. /8 in IPv6 is not nothing like /8 in IPv4. And every protocol that needs a multicast is using that class, like ICMP, neighbor solicitation and neighbor advertisement. It's equivalent of ARP. Or then DHCP is using multicast as well, up to PIM and other multicast protocols. The last class we should be aware of is 16.4FF9B. This class is reserved for mappings between address family. It's mainly being used by NAT64, and it should not be routable outside of provider network. I told you before that the IP address is connected to the MAC address. But first, one big change between IPv4 and IPv6 is that with IPv6, each node that is compliant with IPv6 must be able to have more than one IPv6 interface, IPv6 address on the interface. This is a must. So at least link local, it's also a must. Also, if there is a public address on the network, the device must be able to add that address to the interface as well. There is no upper limit of how many addresses can be on the interface. Also, each interface, each address has a lifetime specified by router advertisement, so that assigned address has an expiration date, something like in the DHCP protocol. Often, the mask is /64. That mask is the equivalent of /24 in IPv4. That mask is mostly used for one layer 2 segment. If you have one network connected to the switches, most likely you will see /64 other mask on it. How the connection between MAC and end of the IPv6 address looks like. So almost every interface has a MAC address assigned. We are switching one bit of the MAC address. We are adding FFFE between the first 3 octets and the last 3 octets, and then we have the IPv6 address here. So we have the MAC address here, and we have ended with the IPv6 address like this one. So first the link local address, then the yellow is the bit switch from 00 to 01 at the end. Then there is 2 octets of original MAC address 13 and DB. Then there should be FFFE, but the Juniper has taken a different approach, and here they are putting the sub-interface number, and at the end 3 big bytes is again the MAC address. This has created some concerns that since the IPv6 is routable, it's a public one. One seeing the source IPv6 address can, reverse engineering, create the MAC address of the original. Knowing the MAC address, we can know what type of device is using. Is it some TP-Link, or is it some China equipment, or Juniper, or IBM? Knowing that, we can create some attacks targeting exactly that type of vendor. So there are some workarounds or different standards like secure or random addresses. Since we are playing with /64, again, we have plenty of IP address to choose from inside one network, and we can adapt, we can change on the fly. How do we assign the IPv6 address on the interface? The first is the router advertisement. So each router, each gateway on the network is sending every 60-second or longer, shorter period, it's not viewable, via multicast information about the network, like gateway address, how to reach the other networks, like prefix, like DNSs, like lifetime of that prefix. So you know that this prefix is valid till or for that amount of time, and if you do not receive any new router advertisement after that, you have to drop that IP address from the interface. There is also big stating that DHCP should be used to get extra information, and if endpoint receives such router advertisement, such packet from the router, it will start DHCP process to get the rest of the information. Second idea how to get the IPv6 address on the interface is to use DHCP. We know most of you know the DHCP protocol. However, in IPv6, it's a little bit different. First, it's using a different ports. Second, client is no longer identified by MAC address. Third, the gateway is not provided at all. The only way to get the gateway is either the static configuration or router advertisement. That decision was made some time ago, since router advertisement provides redundancy, but that field is missing and will not be added. Also, DHCP is not using broadcast. It's just using multicast plus link local addresses, not like in IPv4 networks. The last way to configure the IPv6 address is to use the static configuration. I was talking about the ICMP before, and most of you know that the ICMP is just a ping or tracer or those simple command. In IPv6, the ICMP is much more. First, it's taken a role of an ARP protocol. So there is a dedicated ICMP type, neighbor solicitation. This packet replaces ARP request. It's being using link local address as a source. It's being sent towards specific multicast address. It also used to detect if there is a duplicate IPv6 address on the network. Neighbor advertisement. This is the ARP reply. So this again ICMP v6 packet is being sent in the opposite direction and connects the MAC address with the IPv6 address. I talked before about the router advertisement, but when the router advertisement happens every amount of time. Sometimes it's not enough. Sometimes a customer wants to receive the router advertisement immediately after it's being brought up. In that case, the user is sending router solicitation and it's asking via multicast, hey, gateways, respond to my solicitation request providing the info. In most of the cases, routers respond immediately and are giving the same information as normally, but without the need to wait. So we have some discussion about the IPv6. Now let's talk about transition. Why it's taking so long? Why do we need to wait since the IPv6 is so great? Why it's not widely deployed? Why we are still stuck with the IPv4? First, the IPv4 just works. It has not run out. There are some reserve left. There are plenty of NATs, so people are aggregating multiple devices to use one IPv4 address, and people just thinking it will somehow be, let's put it on the next year budget. Let's not do it right now. Also, there is plenty of hardware and software issue. If anyone of you were using VMware 6E with IPv6, there was a famous issue that the gateway was not able to use local address. Also, there is a chicken. There should be an egg here. I don't know why it's being displayed as a square, but there is a chicken and an egg problem. So there is no IPv6 content. Why? There are no users. There are no users because there is no IPv6 content. Simple chicken and egg problem. Provide us with the contents, we'll give you users. Provide us user, we'll give you content. And those are both on the side of the fences in the IPv6 world. Nevertheless, there are some existing technologies that make the transition easier. On the right, shows that nice world map. You can see in green the countries that IPv6 traffic is exceeding 15%. Poland is not one of them. I think we are around 10%. So we have still some time to become a green one country. But let's go back to the technology. First, there is a dual stack. This is the simplest one. Then there is NAT 6.4, DS9, MAP-T. TCP is not transition technology, but it's a very important protocol. I will discuss it later. And in reverse, when you have only IPv4 connection and you want to see IPv6 packets on the world, you can use 64 tunnels. So, dual stack. This is the simplest approach. So it assumes that each machine has dual stack, IPv4 stack, IPv6 stack. They are using both of them at the same time. One very important thing that you should remember if you decide to play with the IPv6. IPv6 is always preferred over IPv4. So if a host has two ways to reach a destination, via IPv6 or via IPv4, it will use the IPv6 unless it's specifically configured to use IPv4 first. This creates a lot of issue if you start using IPv6 addresses in the network. Most of the machine will transparently switch over to the IPv6 protocol, and you must be ready. And we'll be talking about this later as well. The ideal scenario involves public IPv4 address, although the private one is acceptable. It just requires a NAT or 4 device later in the network provider. DS9. This is approach when customer is connected via IPv6 core. So the customer premise equipment like Livebox in Strada or some modem in UBC. On the one side, it has only IPv6 address. However, the customer has IPv4 and IPv6 as well. How it's being done? First, the customer has dual stack on. It's the user here has a dual stack with the private IPv4 address assigned. If that customer wants to reach IPv6 content, it just goes natively to that content. If that customer wants to reach IPv4 content, then the CPE is taking part of it. So the CPE, which is a gateway for the customer, that CPE gets the IPv4 address, encapsulated that IPv4 address inside IPv6, it's creating a tunnel, then it's sending the tunnel towards the thing called CGN, it's carrier grade NAT. It's something like a NAT on your local home network, but it's being able to serve hundreds of thousands customers at the same time. So it's a much bigger box. On the CGN, the packet gets de-encapsulated, then it's being NATed, the source, private source, is being NATed to the public one, and then it's being sent via IPv4 core to the web server. Response, the same in reverse, so it's hitting the CGN, reverse translation is done, CGN encapsulates the packets back into the IPv6 tunnel, sent to the CPE, CPE de-encapsulate, send the response to the user. This approach is used by the customer home network, like I said, Strada or UPC. It's almost transparent for the user. The user can have only IPv4 stack and still is able to reach IPv4 content on the network, on the internet. The second transition is NAT64. This transition, this method is mostly used in the cellular networks. Also, again, Orange is using one of them. Multiple United States providers are using them as well. In that approach, if there is no CPE, the user is getting IPv6 address here, and how the user is reaching IPv4 content. Since it has only IPv6 address, it's asking for the DNS request to the for the DNS record. It's asking, hey, what's the IPv6 address of the example.com web server? That DNS is doing some magic. It's asking what's the IPv4 IP address. Then it's compiling that IPv4 address into IPv6 prefix, and then it's responding to the customer. Now the customer thinks that the web server is reachable via the IPv6 network. So it's sending the IPv6 packet towards that IP address, 64FF9B. That address, that network prefix, is advertised by the CGN again. It's intercepting that packet. It's removing the IPv6 address entirely, replacing with the IPv4, sending to the web server with response again the same. This works pretty good for the DNS records and the content reachable via DNS. However, the customer must support IPv6 protocol here. There are some content reachable only via the pure IP address without DNS, like FTP, like the IP address inside FTP control protocol, SIP, Skype. They are encrypting IPv4 address inside the payload, and the DNS is not able to solve them. In that case, the customer must be able to support that extension, and in that case, the translation between IPv4 and IPv6 is being done by the customer without the DNS, and the rest is the same. So it's CGN is doing that translation, and it works. However, again, with that approach, customer must be supporting IPv6. Mostly it's being used for cellular phones. Android or iPhones are supporting that approach. MAPT. This is not known. This is a Cisco solution, mostly provided and implemented by Cisco, because Cisco for a long time decided that, hey, no one will be using DS9, no one will be using NAT64. We have a better solution. And we think that the world will follow after us and will follow that solution. Some years later on, they have discovered that the world has a different approach. The world is using DS9, so they were left with no support. They lost a lot of customers with that. But still, MAPT, this transition is interesting because it's moving the stateful part of the NAT into the CPE. Basically, the customer is not getting a full IPv4 address like now. It's just getting a part of it. So it's getting a public address and it's getting the range of the port. So if a user behind the modem is sending IPv4 address, that address gets from this from this source towards this destination, is getting translated directly into IPv6 address, and the source address and the destination address is encoded inside the IPv6. The port is changed because we have only this range to use, and that packet is being sent via the IPv6 network towards some of the devices. Since every information, source IP, source port, destination IP, destination port, is encoded already inside the IPv6 address, the transition on the CGN is stateless one, so it's very, very fast. It can be done, it does not require a service card, it just requires a line card, so it can do with the line rate. It's very, very fast. JPEN is using this, I think, entity is exactly. However, I'm not aware if if anyone in Europe is using the transition. There is a second approach, MAP-E. The idea is exactly the same, however, there is no encoding IPv4 inside IPv6, there is just encapsulation, so there is a tunnel. Still, stateless transition on the CGN is being done as well. I told you about the PCP. PCP is not a transition, PCP is a protocol. With a NAT, having on your own device, on your own modem, on your own firewall, you can do port forwarding. If you want to provide some service on your whole computer like BitTorrent, you just open a port on the box, and every connection towards the public IP or towards that port is being translated inside your own home network towards your PC. This works when you have full control on the NAT and you own the NAT. With the carrier-grade NAT, you do not have the CGN in your home. That translation is done few hundred kilometers, a long way from you. How to control that? There is a PCP. A PCP is a way to inform the carrier-grade NAT that the carrier-grade NAT should open a port for you and do the port forwarding for you. So there is a MAP request. It creates an inbound forwarding. So you just say, hey, I'm having that public IP address. If anything comes to that public address, to the port 80, forward that packet to me, to my internal IP. And the CGN is saying, okay, I'm fine with it, or no, I have no resources for it, or that port is already used by someone else, let's use something different. Anyway, it's some approach to control the provider NAT to do the translation. A peer command, second command in the PCP, is something for reverse. You want to have outgoing traffic translated into specific IP address and specific port. As I told you before, there is some people that want to have IPv6 even when the provider is not giving them a way to reach it. In such case, they can use 6-in-4 tunnels. So they are just encapsulating the IPv6 traffic over IPv4 network. They are reaching some IPv6 provider. The tunnel is ended there. There is then the encapsulation, and the IPv6 inside is being forwarded into IPv6 network. One warning: it's not the layer 4 packet. It's not the UDP, it's not the CP. Mostly it's used layer 3 protocol named with the number 41. It's not played nice with NAT. Layer 3 protocol are not NAT friendly, but most of the Linuxes or devices based on Linux can translate that tunnel into public address. So if you want to reach IPv6 content, you just apply to one of the providers, tunnel brokers, and they are giving you from one IPv6 address up to /48 IPv6 class for your own use. And you propagate that class on your own network, encapsulate the traffic into the tunnel, and it's working. It's free, by the way, so I encourage you to do so. Let's move to our story. Codinine decided to implement IPv6 some time ago. I think it's 2 months, or more or less. The story is built from 4 parts. We requested IPv6 prefix from the provider. We have enabled the IPv6 protocol on our firewalls. We enabled the IPv6 on the core switches. And there are some small things like an on. We moved from the edge to the center. Because the IPv6 takes the precedence, if we would enable IPv6 on the center switches and advertise default route, people will be starting using IPv6. Since there was no support on the firewall, it would be dropped. So first edge, then the core, not the other way around. We requested IPv6 prefix. It's free. We weren't charged for it. We got /48, so it's like 65,000 of /64 networks, plenty to use. However, it's not always available. Our primary internet provider responded on the next business day, giving us the prefix and making the reconfiguration. The backup provider has no support for the IPv6 at the current time, so we are just left with one provider and one network. Then, having the prefix, we enable the IPv6 on the firewall. We are using Juniper, so we added the family inet6 on the interconnecting interface. There is no need to put the public IPv6 there. The link local addresses are just fine for the interconnecting traffic. We have no license for the BGP or ISIS, so we use OSPF here. We enable the second OSPF protocol to advertise IPv6 prefixes. For our surprise, there were almost no changes needed in the traffic policy on firewalls, so we just skipped that part. However, we discovered that first, all IPv6 traffic was dropped on the firewall. The firewalls were dropping the IPv6 packets, so we dig into the documentation, discovered the magical line that will enable IPv6. After the commit, we have a nice warning. You have to reboot the system. So we waited till the night when no one was using our internet in the company. We rebooted the first one, we rebooted the second firewall, and that part was done. Core switches had less surprises, no reboot needed there. Again, IPv6 family inet on the interfaces. Since the IPv6 is a different family, it needs a different protection, a different filter. If someone is using an IPv4 filter to protect access to the switch itself, like only dedicated subnet can connect to the SSH protocol, you have to specify firewall for the IPv6 as well, otherwise you are playing open for IPv6. As before, we have to enable OSPF as well. We have to black hole all prefix on the core devices, otherwise we would have routing loop between firewalls and provider edge. And then we enable router advertisement on interfaces toward the user, and the user start getting the prefixes for IPv6. So, little things. We need to still enable DNS, IPv6 on DNSs. Currently we are using IPv6 request over IPv4. It's working fine, so we have no rush. As said before, IP tables is something entirely different from the IPv6 table. If you enable IPv6 on the server, you have to remember that you have to create IPv6 IP tables rule as well. Otherwise, you might be protected from the IPv4 network. Still, over IPv6, someone can connect to you. As flow collector, to see the flows, it needs to be updated as well because it did not interpret the IPv6 record correctly, and we forgot to inform the user in advance, so they discovered it for us that they had running IPv6. Otherwise, there were no issues. People are using it. It's about 20% of our traffic, and from what I remember, no one was complaining. Now, let's talk about the IPv6 in the hardware. In the IPv6 support on the hardware, on the network device, I'm talking about the telco device, is split into three parts: control plane, forwarding plane, and layer for services like NAT or TCP. Control plane. Control plane is built mostly from the routing protocols or routing services, and those routing protocols are divided into two approaches. Some protocols have integrated the IPv6 protocol regardless of family they are used. For example, ISIS and BGP can have records of IPv6 exchanged even if they are using some other protocols to connect to each other. This is efficient, so both of the information can be exchanged at the same time in a single message. This is faster, so if there is a fault in the network, since there is only one protocol, that protocol informs at the same time about the IPv6 failure and IPv4 failure. However, if there is a bug in IPv6, then it will affect IPv4 prefixes as well. And migration, for example, if you use a BGP with the IPv4 address and you have IPv6 only core, you have to use BGP over IPv6, not over IPv4. So the migration is a little bit harder. The second approach is to create a dedicated new routing protocol. It's RIP, it's EGRP, it's OSPF. Those protocols are native for the IPv6, so we are basically running two sets of protocol. For the OSPF is OSPF for IPv4, and the second similar configuration for the IPv6. So what was the advantage on the previous slide now is a disadvantage. So we have twice as much hellos because we are running two protocols at the same time. Reactivity is a bit lower because both protocols have discovered that there is a failure. Of course, bugs. If there is a bug in the IPv6, the OSPF for the IPv4 is most likely unaffected. Migration is also easier because you have running IPv4 protocols and you are just adding a new protocols and you are luckily you will not affect it with the IPv4. Interoperability. So NFC is taking time. For example, there was a vendor H and there was a vendor G, and there was a VRP protocol. One vendor was supporting final RFC, the other vendor was supporting draft version. Result, both of them were thinking that the second node is dead. They both assigned to them the virtual IP addresses, and they were fine with it. Because in the meantime, between the draft and the final version, the format of the VRP packet is changed. So they were not able to recognize the other node. PCP, the PCP protocol I mentioned before has almost 30 drafts before the RFC, so many years before it reached the final version. So some cases where the CGN was supporting some draft or the final version, while the CPE and CPE can come from multiple vendors, TP-Link, ZTE, others, and those vendors can support either draft, most likely a different one we are supporting on the CGN, or the final version. Again, most of the cases you pick only two options and they are not the one you want to have. Luckily, it was 5 years ago and right now everyone supports just the final version of the PCP, but during the implementation and during the transition of some large providers, the PCP and the draft, that was the case. Communication with the third-party components. The routing protocol is not the only thing inside the IPv6 network. There is a radius communication, there are logs, there are SNMP. If you want to be IPv6 compliant, the control plane has to support connection to those services via IPv6 as well. Router advertisement. That part is interpreted by the host directly. Those are different hosts, Android, iOS, Linux, Windows, etc. So you have to be exactly in line with the RFC to get it working. The second part of the routing devices is a forwarding plane. What has changed here? IPv6, it's longer than IPv4. It's 128 bits versus 32 bits. So each prefix consumes more memory. The bigger address space. In IPv4, we have 4 billion of IP addresses. In IPv6, we have much more, trillions of them. So bigger address space, there is possible to have more prefixes, and then the more prefixes takes more FIB. So again, we are consuming the memory in line cards to decide where the packet should go. Due to above, since the address space is bigger, there is more prefixes to choose. The address is longer, so more memory needs to be searched for. The lookup takes longer. And this creates another issue. Currently, the number of IPv6 prefixes grows. It grows at some speed, and luckily the memory lookup is faster than the current size of the IPv6. So if we have 100 GB interface, each packet can be looked up into the memory, see where it should go. However, with the more prefixes, the search will be longer. At some point, the search will be slower and will not manage to find an exit interface before a next packet will arrive. So this is not happening right now. It will happen in 5 years unless there will be some revolution in memory speed. But there are some countermeasures like Lisp protocol that should solve this issue, but it's in early stage of development. Since ICMPv6 has been improved, that support of ICMPv6 protocol is mandatory, so line cards or network hardware must support the IPv6 as well. Traffic class and flow labels, those are new fields in the IPv6 packet. They are taking bits, 8 and 20 bits, so there is a different approach to QoS or load balancing. Access list or policy-based decision. There are two approaches in network equipment. One is a TCAM, it's memory lookup, or ASIC. There's a dedicated chip that is comparing and doing some logic with the packets. Both of them needs different approach with a different IPv6 standard. On the plus side, no fragmentation in transit, so we can drop that part of the code inside line cards entirely for the IPv6. However, as I told you before, the IPv6 is 20 years old. Even now, some vendors have some issue with it, like a cursive lookup, like VPN over V6, IPv6 protocol is not supported. Both of them are not supported. Both of those issues are hitting the vendor behind our east border. Layer 4 services. This is the last part of the network equipment. So, in the telco world, we have bigger bandwidth. We have 100 gig interface, we have 400 gig interface. So, to support DS9, NAT64 or MAP-T, vendors has developed a dedicated cards, service cards. Juniper was MSDPC or MSCPC, Cisco service card, Alcatel-Lucent, it was a multi-card integrated service adapter. Those are pretty much expensive cards, and they are created only for the reason they are being used only to provide DS9 to the provider. All those services, DS9, NAT64, PCP, they have few things in common. First, they introduced the layer 4 to the network core equipment. Till now, the core network of the telco provider was aware only for the IP layer 3. They were looking at the destination IP address, they were deciding where the packet should go, and they were sending it. Right now, since they are implemented the NAT, they have to look into layer 4 as well. It takes time, since the NAT is stateful, it consumes the memory as well as the CPU. Since those cards are expensive, they must support plenty of users from 10,000 to 100,000 at the same time. There are, with the DS9 in the orange, there are 3 of them for the whole Poland. There are big differences. Also, the PCP has created a way to interact directly with the core devices from the customer. So, the customer can send a packet that will be received by the core devices, it will be interpreted, and some action will be taken. In result, there is a new a lot of security issue might occur since we are permitting customers to deal with the network devices as well. This is the last slide. Who is using IPv6? Well, of course, Google and YouTube. If you are having IPv6 IP address, when you are reaching YouTube or you are using some Google services, most likely you are using IPv6 protocol. Facebook has implemented IPv6 as well. Netflix, Wikipedia, Yahoo, GitHub. For the providers, Orange and UPC, I am aware of those two has implemented DS Lite and NAT64 for the cell phones, Codeline, as mentioned before. From the operating systems, the proper IPv6 support was from the Windows version 7, Linux supported since 2.6, macOS, well, it started with 10.7, it was bugged, so the proper implementation was from 10.11. Android supported IPv6 from 5.0, iOS 4.1. There was some statistics taken in the United States network, and around 80% of the smartphones are using IPv6 natively without any issues. Okay, so this is pretty much that was pretty much the introduction to the IPv6. If you have some questions, I'm open to hear it. Okay. I'm sorry, I'm not knowing your name. Marcin.
Z mikrofonem bez? Wyraźnie?
Tak.
A jak z VLANami? Jak mamy VLAny w sieci, czy segmentacja i chcemy to na firewallu jakoś zabezpieczyć, czyli taki najczęstszy przykład, a wszystkie komputery w sieci mamy już po IPv6. Jakieś problemy z tym? Czy po prostu...
VLAny są całkowicie niezależne na innej warstwie, więc...
Właśnie pytanie o firewalla. Jak właśnie z firewallem?
Jeżeli przy firewallu masz dokładnie ten sam problem co przy czwórce. Jeżeli masz jakąś filtrację na czwórkę, to prawdopodobnie na szóstkę ona się nie przynosi. Szczególnie jeżeli chodzi o ochronę samego firewalla, czy dostęp do SSH. Jeżeli wdrożysz szóstkę, to musisz założyć filtr także na szóstkę.
Inaczej zadam pytanie.
Dobra?
Bo rozumiem, że trzeba, korzystając z wielu VLANów, a otrzymując od operatora jakąś pulę, to tą pulę wykorzystuję tak, że u siebie w firmie na własne kopa i rozumiem, że muszę to posegmentować na znacznie mniejsze podsieci do swoich VLANów i
tak.
Po prostu w ten sposób jak zawsze, tak?
Dokładnie. Od Orange'a na przykład dostajesz /56 jako użytkownik domowy, czyli dostajesz 256 publicznych sieci, które możesz wykorzystać, czyli 256 64. To jest dużo. Więc tutaj nie ma problemu i dostawcy bez problemu dają duże klasy szóstkowe, tak żeby ci nie było problemu, że musisz jakoś oszczędzać czy segmentować. /64 dajesz na sieć i jeżeli masz za małą, prosisz dostawcę, daj mi więcej, a szóstek dostawca nie robi żadnych problemów. Jeżeli chodzi o to, że szóstka jest publiczna zawsze, to większość firewalli po prostu podchodzi do tego stanowo. Wypuszcza ruch na zewnątrz, ale ruch powrotny puszcza tylko ten, który jest established albo related. Czy to jakby... Woda? Dobra. Paweł, widzę, że miałeś pytanie.
Kiedyś szkółka wychodziła i rozdawaliśmy wszystkim adresy. Myśleliśmy, że wystarczy, było ich miliony. Teraz mamy ich miliardy w szóstce i dlaczego myślimy, że miliardy nam wystarczy? My kiedyś myśleliśmy, że miliony nam wystarczy.
Są porównania do ilości mrówek, atomów w wszechświecie i tak dalej. Tej szóstki naprawdę jest dużo. Są oczywiście IPv6-12 jakieś RFC, ale zróbmy na razie szóstkę i sądzę, że to nam wystarczy na kilkanaście, 10 lat spokojnie i zobaczymy co dalej. Na razie nie ma ryzyka, że szóstka starczy, bo naprawdę są gigantyczne wartości.
Okej, a pytanie o performance. Jednak szóstka ma dłuższy adres, jak radzą sobie z tym routery, które przeszukują tablicę routingu, jednak jest trochę więcej bajtów do przeszukania.
Tak, więc masz dokładnie sytuację, że większe bajty do przeszukania, większy rozmiar, dłuższy lookup. Jak na razie wydajnościowo są bardzo zbliżone, jeżeli niezauważalne różnice, więc tutaj nie ma problemu. Problem pojawi się, kiedy tych prefiksów będzie tak dużo, że przejście po drzewie wyszukującym będzie zajmowało tyle czasu, że kolejny pakiet już będzie czekał w kolejce i pukał do drzwi, że ja też potrzebuję być obsłużony. No i wtedy będziesz miał problem. Na razie jest tak, że jeżeli dochodzimy do granicy, to jest jakaś rewolucja, jest nowa generacja pamięci, która jest szybsza, znowu schodzimy poniżej. i jakoś gonimy tego królicza. Jest protokół list, który agreguje szóstki w jakieś ekstraklasy, coś trochę zbliżonego do MPLS-a, ale nie do końca i on rozwiązuje ten problem częściowo, ale na pewno supportuje to Cisco, to też na wszystkich urządzeniach, więc to jest, ludzie się zastanawiają, widzą problem, natomiast wszyscy podchodzą, wdrożmy najpierw tą szóstkę, a dopiero potem zaczniemy się zastanawiać nad jej problemami, bo nie wykonuje się jeszcze kroku numer 1. Michał, opowiem. Marcin.
So I have a question about IPv6 headers. I think last time I heard you talk about IPv6, you said something about extended headers.
Yes.
So I'm curious, today you said that the place of every field is stable constant and doesn't change, and that this makes it easier to interpret everything. How does that go with the extended header?
There is a next header field telling you what header will be next. It might be TCP, it might be UDP, but it also might be information about fragmentation. So basic information for the routing is in the base IPv6 header. Extra information is just informed here. What for the routing, in most of the cases you only need what is here, but if you want to extend the header with extra information, you just add information that the next header will contain extra information, and you attach header after header, and then there is content.
Does it move the source address?
No, that part is fixed. After it, there is a next header. Like in IPv4, there is an IP header, and UDP is after it.
So is it like a linked list or something? That it just makes next header, next header, next header?
Yes.
Thanks.
Marcin?
Pytanie przykładowo, gdy mamy 100 jakichś placówek w naszej firmie, powiedzmy, i do każdej dostarczamy jakiegoś operatora, wielu operatorów w różnych miejscach, powiedzmy Polski czy Europy. Od każdego musimy pobierać adresację IPv4, czy wystarczy tak naprawdę mieć jedną pulę dużą IPv, przepraszam, szóstki, czy musimy od każdego operatora dostać jakąś IPv6 również?
Znaczy to zależy, to podobnie jak z czwórką, jeżeli masz BGP i masz wielu dostawców, to możesz mieć jeden prefiks i rozgłaszać go przez BGP. Jeżeli nie masz BGP, to tak od każdego musi dostać osobny prefiks jak czwórkowy i już wejdą do tego połączenia.
Rozumiem. I wtedy VPN-a i tak dalej.
Tak.
Na prezentacji pokazywałeś, że przy waszego wdrożenia budowaliście dwa routery, przełącznik i komputer. To też jakieś segmenty, które wspierały usług. Jakie narzędzia, produkty, oprogramowanie i z jakimi problemami spotkałeś się w obszarze cybersecurity? Dlatego, że one w ogóle nie były zaruszone.
Dobre pytanie. Zastanawiam się, jak ci na nie odpowiedzieć. To na pewno. Nasz stack jest troszkę specyficzny. Na przykład usług w naszej firmie jest bardzo mało. Mamy OpenStacka, który nie jest w ogóle zaszustkowany. Tak naprawdę obsłużyliśmy bardzo proste przypadki, dostęp do internetu i podstawowe usługi, natomiast nasze usługi nie są wystawione na światło szóste, ponieważ większość naszych usług zewnętrznych trzymamy w chmurze. Więc duża część nas ominęła. Druga sprawa, większość naszych stacji roboczych to są Linuxy, troszkę inne podejście do cyber security, ale nic nie zauważyliśmy jeszcze, albo nic nie podniosło naszego zagrożenia. Generalnie firewall, tak jak mówiłem, puszczały tylko wyjściowy, a powrotny tylko established, więc jesteśmy tak jakby za nami. Tutaj dużej różnicy nie ma. To, że ktoś ma publiczny adres, nie znaczy, że jest z automatu osiągalny. A większość maszyn jest na tyle zaktualizowana, że jakieś poważne robole w samym stosie już ich nie dotyczą. Jak na razie nie odkryliśmy, nie znaczy, że czegoś żeśmy nie przegapili.
Okej, a monitoring obszarów lub inspekcje ruchu ekonomicznego?
Tak. Tak, no, na przykład tak jak mówiłem, SEO wymagało trochę update'u, bo widziało wszystko totalnie coś zerowego. 1IDS też, nie, on nawet transparentnie to obejrzał. Nie było problemu, bo generalnie wszystko nas to jest albo GitHub, albo Google i powiązany content.
Wiedziałeś na jakby o naszym wdrożeniu, że mamy łącze podstawowe i zapasowe. Zapasowe nie ma obsługi IPv6. Co się dzieje w wypadku failovera?
Nie ma. Jeżeli padnie podstawowe, to mamy szóstki. Jeżeli padnie podstawowe, tak naprawdę powinniśmy wygasić cały routing w sieci. Jest to bardzo fajny przypadek, który trzeba było przetestować u nas w firmie, jak się to zachowa, bo mam wrażenie, że tak się nie stanie. Więc tak, dobry przypadek do przetestowania, bo niestety też nie mamy BG, ale dla czwórki byłoby troszkę podobnie, tylko dla czwórki nie dajesz adresacji klientom, więc to sobie się sprzątało na inny adres. Dla szóstki po prostu powinna zostać wygaszona. Jest coś takiego było adresacji. Router Advertisement. On ma coś takiego jak lifetime. Technicznie, jeżeli zgasisz szóstkę od providera, nasze gatewaye powinny wysłać router advertisement z lifetime'em 0. Każdy klient dostający taki pakiet natychmiast ma obowiązek wyrzucić adresację z tego prefiksu i przestać używać adresacji IPv6. I to jest właśnie w tym celu, jakbyśmy skreślili komunikację.
Ostatnie pytanie. Rozumiem, że w chwili, gdy mamy w jednym oddziale już oczywiście IPv6, z zewnątrz nikt się do naszych użytkowników nie może dostać, jak rozumiem.
Tak, jest założenie.
Takiego założenia używamy. Więc zostaje nam tylko regulacja na firewallu dostępu, żeby jednak któryś z tych IP-ków były dostępne. Na zasadzie, nie wiem, standardowo byłby to jakiś NAT, czyli forwarding.
Nie masz NAT-a, nie masz używanego NAT-a na szóstce, po prostu puszcza, czy komunikacja do tego adresu IPv6 jest permit.
Czyli tak naprawdę to, co mówiłeś o establish tak, to jest po prostu jako domyślna polityka firewalla.
Domyślna polityka firewalla, że puszczasz szuk powrotny, a jeżeli chcesz puścić coś z zewnątrz, to po prostu nie otwierasz portu, tylko po prostu mówisz, a do tego adresu publicznego puszczamy i zapraszamy.
Bo brzmiało jak jakiś feature nie pokazany na prezentacji,
nie, to jest
pytanie.
Dobrze.
Firewall.
Tak, Pawle.
Planujemy VPN-a po
Co, nasz protokół VPN-owy dość dziwnie podchodzi do szóstki w paru przypadkach i to wymagałoby troszkę ostrożniejszego podejścia, ale czemu nie? Możemy być brokerem dla szóstki dla naszych pracowników.
Żeby używać translację na czwórkę, czy na przykład chcielibyśmy udostępnić sobie zasoby
Nie, bo prawdopodobnie po VPN dostajesz obydwa adresy, i czwórkę, i szóstkę. Musimy wyłączyć czwórkę, żeby ich zaczął dostawać, żeby się odbyła translacja. Tak naprawdę to jest za dużo roboty, dostaniesz i szóstkę, i czwórkę po VPN-ie i będziesz używał tego, co ci DNS rozwiąże. To jeżeli nie ma pytań, to...
Jeszcze przez to w DHCP jest identyfikowany klient, jak nie przez Maca?
To się nazywa DUIT, to może być MAC, to może być timestamp, to może być jakaś dowolna własna informacja, jest to ciąg znaków.
Okay.
I to jest zmienne w zależności, w którymś nagłówku DHCP jest podane, czym jest DUIT, czy to jest MAC plus czas, sam MAC, stringi unikalne, czy coś jeszcze innego. Jest ileś odpowiedzi.
Okay.
Jeżeli nie ma pytań, to dziękuję za uwagę.
Wszyscy są na miejscach, mam nadzieję. Zapraszamy do naszej drugiej prelekcji, którą poprowadzi gość Konrad Gawda. Przekazuję mikrofon.
Cześć wszystkim, dzień dobry. Będę mówił o czymś, co się nazywa P4. Ale najpierw 3 słowa o mnie i te 3 słowa to będą 3 pasje techniczne, jakie mam. To jest sieciówka, jest programowanie i to jest elektronika hobbystyczna. W momencie, kiedy pojawiło się w świecie telekomunikacji hasło wirtualizacja, byłem bardzo zadowolony, bo te dwie pierwsze z moich pasji połączyły się. Okay, and now I'll start again for all the English speakers. So, hi, hello, my name is Konrad Gawda. I will talk to you about P4, and before that, 3 words about me and my passions, and those are network programming and embedded electronics. And somehow, they all find their place in P4. But before that, P4. There is a company called P4 that is a mobile operator in Poland, and this presentation is not about that. So I have nothing to do with that company. This presentation is about P4 programming protocol independent packet processors. And why it's important? Okay. Why it's important? Maybe I'll stand in a different place. Well, first of all, it allows you to do things with the networking hardware that were not possible before. So it opens programming possibilities. Of course, for the users of the hardware, if you're a hardware manufacturer, you can manufacture still what you want. But it opens the possibilities for users. On the second place, it gives great performance because you could do different things in other technologies. But this one gives a great performance. And the third one, which is not obvious, is simplicity. Although the language is complicated, in some cases, it is really simple. To start with that, we'll start with 2 things that are basis for understanding P4. And one of them is this picture. This picture, which is a real great simplification of how networking devices, switches, or routers look like. So basically, there is CPU like in a computer, but there is also another circuit, another integrated circuit that is the horsepower of the device. So it's not as versatile as CPU, but it has to push the traffic and do it fast and in great quantities. And there is interface between them so that CPU tells the packet processor what to do. And that's the very old classical idea. Then came SDN and OpenFlow protocol. So with that protocol, the main idea was to free the interface between the packet processor and the CPU, and to give the world open protocol that can do this communication, that can leverage this interface. So from the packet processor, we get the whole device that is called OpenFlow switch, and we get some controllers which take the role of the CPU from the previous image. So basically, you can have any controller as you like, write an application, and there is interface so that the controller takes the switch, talks to the switch and says what to do. And I mean, configures the packet processing unit, insert rules, insert values in the tables. And another example, another picture of P4. So there are some flow tables. In fact, in first version of this is still about OpenFlow. In the first version of OpenFlow, there was only one table, one match action table, and then some actions were called. And you can populate those tables from the controller. Okay, so what's inside? What can we do with those tables? What kind of matches in the tables and matches and actions can we act in those using those tables? Well, OpenFlow is really great about that. I mean, it implements a lot of matches, and you have the Ethernet, VLAN, IP, TCP, and so on, matches of different fields, and it also implements actions, so you can manipulate different fields. And while the standard is growing, next versions cover more and more of those fields and actions, so it makes them more versatile. Still, for example, in the first version, there was not even a good support for IPv6, so this is something that the standard had to reach by growing and increasing its versatility. Another thing that I would like to mention before going straight to P4 is white box approach. So the idea is, okay, we've got a switch, it has a CPU on it, let's allow users to insert any operating system and software that you would like to do, to launch on that device. So what we've got here is, of course, some chassis which is common for the whole equipment, and then we got CPU, and in parallel the packet processor, packet forwarding chip. So on this CPU, you as a user launch some operating system that is comfortable for you, with set of applications that you would like to, that will cover the control plane, and we will tell the packet processor what to do using some drivers. Because if you have the packet processor here, there are drivers on top of that. And to make it simple, there are some abstraction layers. And switch abstraction interface is one which is thought to be quite good, quite useful one. So this is an approach to make the networking devices more open, to allow users to take benefit from them and do different things that the device was not strictly designed to make them more versatile. And well, P4 is exactly about that. And I will use this analogy, which perhaps you may have seen, which is used to explain P4. So the story goes, if we have CPU on the computer, for example, there is a programming language and a compiler that produces the machine code that then can be launched by this processor. The same for graphic processing units. So there is a special language, there is a compiler. For DSP, digital signal processing, the same, there are languages, compilers. For Google's tensor processing unit, there is a language, there is a compiler. But still, for the packet processors, we didn't have this situation. We were only able to insert some rules, some values using this interface via driver. Here comes P4. So, okay, it's a little bit cut, but you can see that with the networking device, the idea is that P4 is to be the language for programming the packet processor. This integrated circuit that sits in the device, and there will be some kind of compiler for that. Okay, so now I will talk about how it looks like. What are the ideas inside P4? So there are some basic blocks that we need to use. In fact, we even don't need to use. Only one thing is optional. One thing is really needed. Most of them are optional. All the things that are in this picture are optional. But let's dig in. What are they? So we have parsers. We have mesh action tables. We have something called traffic manager and a deparser that is, of course, something like parser, but made the other way around. And those are only the blocks. Each device might have different amount of resources that can be used. And there is also something more. There is metadata pass, there is API, and there are externs. So I will mention those later. But now let's focus on how does it work, how to program that device. Let's jump in for some code. That's, I guess, the most interesting part. So, I hope you can hear me well right now. Yeah, I hope. Okay, great. So I've opened the link from the presentation, and we have very basic thing. Well, basic, but working. It's a layer 4 switch. And if I open the code, I see it's quite similar to C programming language. There are some includes in the top. I see there is something about V1, and this will be important later on. But let's scroll to the beginning. So we've got some types, okay, different numbers of bits for different addresses. Sounds cool. Then headers. So we have Ethernet header, and IPv4 header. So as you see from this example, with P4 you could handle any protocol, any type of header. I mean, it's not limited to IPv4, IPv6, or any other version that will be found in the future, as long as it can be expressed in bits and bytes. And this one is quite important because it's a structure called headers, and it combines those two. And there is some more code later on, but that's how it goes with reading C code. Okay, the type that's okay, but then there are some functions. So typically what you do, you go to the bottom and try to find when the main starts. So I scroll to the bottom, and we're lucky because main is just really in the bottom. And this is a cool place because in the really bottom of this file you have all the functions. In fact, they're not the functions, they're called controls that the packets will traverse. So you see there is a parser, there is a checksum verification, ingress, egress, there is a checksum computation, and deparser. So let's see how those tables look like. So those are match actions tables. So we have a table, we have different entries here with the default ones on the bottom, and you populate this table using control plane. Well, really this is the place where you say, okay, I thought the device will populate those tables magically itself. Well, at least not the packet processor. It needs the data from the table to be populated by the control plane, by some controller. So exactly the same as with those other approaches. But let's go on. Let's see the interesting things. So we have a parser, and the parser gets the incoming packet and extracts some information, gives some meaning to that. And this comes to the key column. It's compared to different things that are inside the tables, inside this table. And if there is a match, or if not, then from the default column, action ID and action data are taken. And this decides what kind of action will be launched and with what parameters. Beside the parameters from the table, there are also headers and metadata. And metadata is a not magical, but philosophical things in P4. There's other things that are available all the time while you're processing the packet. Like, for example, the input port number. Okay, this comes to action that is launched, and then the action can influence what will follow later on. For example, change the fields that will be populated. And that's example table. That's example table. So it's got a key, and here are the IP prefixes. Then it has got different actions, and for some of those actions, it got extra data. Let's see the code. Okay. So we finished going from top. We finished with the headers. We have some headers here. Let's see the parser. And in fact, parser is a strange thing here because it's a state machine. It's a finite state machine that you describe here, describing states. So it's not like normal C programming. It's rather declarational, so that you declare what are the states of the parser, and we always start with the start state. Guys in the back, can you see the code? Or? Yes. Great. Okay, so we start with the start state, and then there is a transition keyword, and it gives the name of the next state. This time it's simple, it's parse Ethernet, but when we come to parse Ethernet, then we see two things. First, it is extract, and extract works on a packet that was coming in, and it extracts Ethernet header. And no need to define how we really do that. Before, compiler only needs to know how the Ethernet header looks like, and it automates the extraction of that. Then we transition to a state. Which one? Well, it's a select, so like a case, and we use the field that we extracted a moment ago. So Ethernet type dot ether type. And here we have the ether type of IPv4. Then this next state is parse IPv4. And the default state, if there is no match, is accept. Accept is not defined here. That's just the name of the state that finishes parsing the packet. So you see that this is the place where IPv6 as a type will be placed. Okay, and parser finishes in this moment. Verifying checksum is not done in this example, but then comes the most interesting part, the real hard work here. So what we got here is my ingress control. It defines some actions inside. So those names will be used in a moment. Then it defines a table. Table here has a key which is header.ipv4.destination address. And no need to make any extra reference. The compiler just knows that we defined such field, we parsed it, so it will be ready for use. Then later on, we've got actions that are possible to do. Size of the table and the default actions. Default action is needed, otherwise, or perhaps there are some defaults, but the idea is that if the table is empty, then the default action will be called. However, doing all that, not yet anything done. There's the table, but it's not linked to anything. We need to apply something, and that's the code continues with apply. If the header IPv4 is valid, so meaning if the parser found it, then apply this table, the table that we IPv4 LPM, IPv4 longest prefix match. So that's the table that we define. That's the name of the table. And so in this example, we like a moment ago, we saw the table with some prefixes. We know that the type of match is longest prefix match. So if the packet comes, the apply block is applied. It says apply table. The table is applied. Let's say it found the IPv4 forward, and then IPv4 forward is called. well with some arguments. And we don't really see anywhere here calling the arguments. Where are they? And the tricky thing is that they are taken from the table, from the value part. So that's done automatically by the compiler. So if you see action data here, so this is what comes directly to this action. Okay. One more thing to have a good picture about that is that the physical structure versus what you program, it's not exactly the same. This is the happy part of having a compiler that, for example, if a table is too large, like that one, it can be spanned over different physical devices, resources of the device. So, and we will see that it's quite an advantage here when it comes to use cases. One thing is needed to understand this kind of programming is that in fact you cannot stop. It's not a place when you can stop and wait and think, or you can call some loops. Loops beside parser are forbidden. It's that the idea is that those devices will have line rate. So if the packet comes in, it needs to go. It won't stop unless we want to treat it in some extra way. But typical packets go through that. So we program parser, and in the other parts in the other parts of the code we define what's done on the next steps. But we cannot go back. We cannot do things like loops or recursion, because this packet needs to go through. So in each step, you have the packet with parsed fields. You have the metadata that I've shown in the previous slide. It's available because it goes with the packet. And while the packet goes here, perhaps another packet is followed. So let's go to the API, and because I told you that those tables are filled by control plane, and I mentioned that in other implementations, other approaches, there was an OpenFlow protocol to manipulate those tables. There was some API for the switch abstraction interface. Well, and for example, for OpenFlow evolves. It has new fields, new match and actions possibilities, and the protocol for that evolves. And here, well, you have new match and actions. In fact, anytime you compile the new version of a code. So when you compile a new version of a code, you get the new definition of API. And there is a file that is produced by the compiler that defines this API, and it uses protobufs to do this definition. And then in most implementations, typically gRPC is used to expose this API. And this can work in a way that is typical for OpenFlow, that there is a device and it exposes the interface, and then from some other controller you control that. Or why not? Could be all in the same device, just as I told you with the Y box. So there is the server inside, and the control plane also inside, communicating with the API. Okay. Now we talked about how it works. Now a while for warning. There are some tricks here. P4 has versions. And if you haven't been working with P4 yet, good for you, because you skipped P4 14. which was the initial version, but it got its successor before 16, and that's similar like with Python 2 or 3. They are similar, but there are differences, there are different keywords. Everybody says P416 is much better, so good for us. One of the things that was introduced with P416 were the target architectures. So in the initial version, the P414, there was no such thing like special target definition. So all the switches should work in similar manner, and meaning that if you write some code, you can share it with, it works on all the switches, all the devices. Well, the guys that defined the language discovered that it won't work that way. So they made it work. They made our lives better because P4 is gonna work better. But unfortunately, they also gave us some problems because you cannot write one code to run on all devices. They have different architectures. An example, V1 is the architecture compatible with P414, and this is also an architecture of the PMP2, and this is the development, the software switch used for development. If you would like to test something, go to the tutorial, you use that one. That runs in the software and has nothing to do with performance. PISA architecture is the one used by Barefoot company, and that's the only vendor that I know that produces the integrated circuits that are really programmable with P4. So there are such circuits, there are such switches, and those packet processors work at full line rate. So I found it really really cool. And there are also other architectures. There is I list here one of the architectures that is typical, that is designed to be used for FPGA. And beware, those architectures might have different components inside. So I said about parser, I said about those match action tables, the parser. I didn't yet mention in details the traffic manager, but there might be placed in a different order. There may be repeated like that, and there may be some other variations. But moreover, those architectures can expose different things, like for example, the control of the traffic manager. Traffic manager is the tool used to queue packets, is the tool used to replicate packets. So for example, you see it could be in the end, it could be in the middle, and it needs some way of communicating with your code. And this is with metadata. So you set some fields in the metadata that later on arrive at the traffic manager, and the traffic manager does the job. The possible jobs might be different depending on the architecture. Another thing that appears in P416, and this is different between different architectures, is something called extern. And extern are extra functions implemented in the switch. And that could be anything. That could be a function to calculate checksum, some specific checksum. Would it be MD5 or any other? It could be random number generator. It could be a function that makes some advanced calculations or really simple ones. It's anything that you'd like. So there is in the language, now there is the option to describe what are the extra things made available by the hardware, and you can use that. But still, you can use them on one architecture or another architecture. The core of your code may be the same, but the functions that will be available will be different. So you may need to align with that. And those when I showed you the code in the beginning, there was this import v1 something, and this was exactly the importing of this v1 model, this v1 architecture. So let's think about what can be done with P4. So there are different things that people do and implement there. So with load balancer, with congestion control and congestion notification, with inbound telemetry, caching, and even usage for map reduce. And there are many more. What I will only describe some of them. So one thing that seems quite interesting is the inbound telemetry. And well, basically, it's the idea that on these network devices controlled by P4, programmed by P4, you could insert some small extra header that writes down different information, not only the name of the switch, the time, the rules it used, and one also important thing, queue occupancy. How long is the queue, and perhaps which other flows were in the queue. If you drop packets, that's really handy information. So packet could collect that, and on the last switch that's under your control, you just read this information, drop them, and send to another host, your analyzer, and the destination gets the original packet you wanted to get. Okay, some other thing that was mentioned by use case and was quite surprising to me is simplicity. Make simple switches. The idea is that typically today, if you buy a switch, layer 4 switch or router, it has many functions. So you typically won't use all of that. You will use some subset, and you will turn off everything else. Or will you? Perhaps you would leave some of them on. And this, in fact, could be a security breach. You have something on the switch that you don't really think about, but the function is still running. So the idea is about you take the code that you would use for a full-blown switch, and you comment out the things that are not needed for you. So one thing, you block the unnecessary functions, so you gain on the security aspect. The other thing is also you free some resources. So as I said, those tables, for example, can span different physical resources. So you can gain memory for the functions that you need. Now, before going forward, I wanted to share with you my personal idea how to compare different things that happen in the industry and how it's going. Where is OpenFlow? Where is NFV? And where is P4? So if we take that plot and we make performance on one X and elasticity on the other one, and elasticity, I mean here the elasticity for the user of that device. So what can I do with it? So okay, the classical routers would be somewhere here. They have functions. Maybe not close to zero. Let's say it would be somewhere there. They have some features. You can turn them on. You can configure them. Okay, quite well, and you get great performance. Everything is line rate. Then comes OpenFlow, and OpenFlow says, okay, there are some lower level features that you can use, and you can not only configure but insert rules, insert data and values, match and actions. So with the same performance, you increase your elasticity. So you're somewhere here. On the other end of the road, if you want to do something really strange with your data, well, I guess there were people that were doing some data plane manipulation on computers, on servers before, on PCs. Then someone came with the idea of NFV, so not only give a name to it, but also standardize the architecture and put it in a blocks that will be useful for telecoms. So I think NFV starts somewhere here because you have CPU, you can do whatever you want. The performance, well, the performance is a topic. So people in the industry started digging the problem, and from not so high performance, we've got GPDK and other libraries that accelerate that. So in fact, it came somewhere here with all those acceleration technologies for NLP. And now let's think, where is P4 in this example? So it is not to have line rate, at least for those examples that I know of hardware implementations. So it will be somewhere here. But it will be quite programmable, much more than OpenFlow. So I will place it somewhere here. Could there be something better? Well, perhaps I guess FPGA could be the king, because you could do virtually anything. If you fancy enough, you can implement x86 processor and FPGA or anything that comes to your mind. On the other hand, it's really fast, but it's damn expensive. So for me, this landscape looks something like that. So there is the one approach is having great performance to make it more elastic. The other one is having the great elasticity work on performance. And I would say P4 is somewhere here, because it's quite elastic. I mean, you have the programming language, and finally for the packet processor, you can define what it does. And on the other hand, it should be quite fast. Okay, we're here. I mentioned NLP and programming your servers, your computers to handle the traffic. And in fact, it's not rare things that thing we do every day, at least to have virtual machines and need to make them talk to each other. There are different solutions, but nevertheless, you do different things, programming the software to make it move the packets, to do the data plane. And one view on these P4 languages that from talking to my colleagues is that it is really simple language. Comparing to implementing the whole function in C that will handle packets and writing the parsers, queues, everything. If you could just define what you need using P4 and then have a framework with compiler that will produce the binary, well, that's a great simplification. And perhaps the same for FPGA. If you want to process some packets on the FPGA, it's you could do everything in some HDL from the bottom. If you have some framework that you produce the binary for the FPGA, just using the domain-specific language, that's something that simplifies the programming. So it's easiness of programming. Okay, I will have a time for questions from you, but two questions from me to the language. So, for what is P4? So, one of the things that is challenging for me to understand in this idea is how to handle packets payloads. So, you do many things with headers. Before is about headers, but how about manipulating payloads? So, for example, Fane mentioned here IPv4 fragmentation. Hopefully, we'll not need to do that in far future, but today we do. And my current understanding is that depending on architecture, the traffic manager can handle the payload differently if you set different things in metadata. Well, perhaps it's something useful, or perhaps this kind of payload manipulation is not the real use case for P4. I don't know. The other question is much more high level, and that's about let's say about business model. I mean, I say, well, we users of the devices, but in fact, typically the user of the devices is a telecom company or a data center host, and they're not really embedded programmers. So there's one more category, Google. If you're Google, you will have tons of programmers for everything, I guess. So there will be people coding in P4 directly for the switches that are used in Google data centers. But for other types of companies, well, I guess sooner or later they will need some kind of vendor or multiple vendors for different functionalities on the switch. So vendors of the P4 code or binaries, and there is no really model like NFV was all about that. That was about you got the VNF descriptor, and then manager and orchestrator. So there was all the tooling about launching things from different vendors. And here, this time it comes from the other way. This thing is not yet defined, but I hope it will be defined, because it's easy if you have a technology that is still growing. I think there are things that can be done in this direction. Okay, so I tried to describe fast what is P4, more or less show you some cool things about that. My goal was not to convince anybody that it's a great thing, but just to make you understand what is that. I personally think is a great thing, and also to show you some good sides of it. So, because that's a topic that maybe some of you know it well, I know. Some of you heard about that. Perhaps some of you don't know it at all. So I will now ask you for questions, but I suggest to start with the questions, things that you don't understand, or things that you do understand but think was missing in the slides, and others could not, perhaps not understood. So, please, any questions about that?
Can we parse over the payload?
No, we cannot parse the payload. I mean, a workaround is just to define a header and parse the payload as a header. But that's the limitation.
Is there any support for variable length headers?
Yes, there is support for variable length headers. In fact, otherwise parsing IPv4 would be quite a problem. With only example, we've seen really basic stuff, but there is a special construct for this that you can for variable length headers, and you can read a variable, one variable, or parse one variable, and based on that define the length of some other field. And also the mechanism that is close to that is the variable length length of stacks of headers. So you can define array of headers, like for VLANs or MPLS tags, and you define the maximum length of that table, but it doesn't need to be populated as a whole. And this is the place when loop appears in P4. So parsing function can return to itself to parse yet another header, but of course there is the limit of loops, limited by the maximum size. But you can do that here. You can do loops later on in machine actions.
Is it already used commercially?
Is it already used commercially? People say there are some usages, but I personally don't know. For sure, Google is interested in that technology. It does presentations about that, and it makes calls for vendors to produce such switches. So I guess they use it to some extent, perhaps some modification of that. But I didn't see any official press release from anyone yet.
Is there some kind of developer environment? Like you can simulate a switch on which you can use your program or something like that?
Yes, there is development environment. If you would like to start your journey with P4, in fact there is a quite good environment for that, and you can just download the virtual machine with configured compiler, simulator, and editor with plugins for highlighting P4. And the page I've shown, it's quite easy to find what we are Googling. This was part of that tutorial. That's a solution for one of the first tasks in the tutorial. This environment uses this BMV2 virtual P4 switch, which is designed to be used for development purposes. I heard there's some new version of that using containers instead of virtual machine. Still virtual machine may be useful for some. But well, yes, there is quite a good development environment.
Do you know the pricing of barefoot switches in comparison to Cisco and Juniper, Arista guys?
No, unfortunately, I don't know the pricing of the barefoot switches. No, I didn't check that because I couldn't afford that personally, even if it would be a cheap router. Nevertheless, there is a design in OCP, Open Compute project. So the design of such switch is the whole device is freely available. So you could also order one in China if you're going to use that a lot, and that should be much cheaper.
You showed in one example that we can add the header, so you can add some information to some packets. This is in the payload or in the files?
Okay, so yes, I showed the example with adding extra headers, and in fact, P4 version 16 is cool with that. And why? Because there is parser and there is deparser, and there are separate blocks of code. And this is why you could parse data in one way, but then while deparsing, add extra headers. And is it a payload? Well, it depends how you parse that. But generally, it's an extra header. If you know how to parse that, that's definitely a header. If someone doesn't know how to parse that, perhaps that would be seen as a payload. But that only depends on the way how you design it. Where do you put this header on in which part of the stack?
So can we use some random packets data plane to moving some information between the switches, like route advertising?
Okay, I'll repeat the question. Would it be possible to use any kind of packets that go through to ship some information between switches, like route advertisement? Well, yes, that's possible. Would that be good? Would that make sense? Well, I guess some people could argue, but that all depends on a case, and technically, yeah, that's fully feasible.
On the slide with performance versus elasticity, you show that the PDK is very elastic, or the performance isn't there compared to before. Have you looked into solutions like Metronome, SmartNIC, which is basically offloading the PDK to the card itself, and does it bridge the performance gap between those two technologies?
Okay, yeah, I really, yeah, that's true. I've shown NFV and then higher up NFV with the DPK, so it has boosts the performance. And the question is about SmartNIC, like from Metronome. That really depends how the SmartNIC is designed, because some SmartNIC just use FPGA, so perhaps you're not that high or you move somewhere there because it is limited in size. Some SmartNICs do it different. So for me, using the SmartNIC is a bit like taking a piece of switch and installing it in the server, and then that would be a good exercise to try to map different kinds of SmartNICs here. But no, I didn't exercise that. But I guess there would be several positions to place that.
How my P4 program can communicate with external world? So, for example, I would like to change the behavior of my program on the fly. So, for example, in configuration. I don't know how he adds some headers or something like that.
Yeah. Okay. So you can how to communicate with the P4 program that runs in a switch. I mentioned the API. That is automatically generated each time you compile the code, and then there is some server, typically with gRPC, on the switch. If I remember well, beside match and action fields in the tables, you can also modify some variables that are global for the switch. So to modify the way the switch behaves, you could just write in the variables to define that. The communication in other way is a bit more tricky. If you would like to send a packet from the switch to the controller, that, from what I understand now, is target dependent. I didn't dig much into that, but it's not the first thing that you will meet in the tutorial for sure. Yeah, any questions from that part of the room? Okay, let's check the time. Well, I guess we're perfect. So we came through all of that. I hope you not only understood the P4 language, but perhaps you even like that. I hope so. I hope it will change the world a bit into a better place. Thank you.
Podziękujemy brawami Konradowi. Adama już niestety chyba z nami nie ma. Natomiast ja zapraszam Was na ostatnie tego wieczoru rozmowy w kuluarach i już teraz bardzo Wam dziękuję za uczestnictwo. Dzięki.